Hey everyone, today I wanted to show you some Tensorflow. This code that I'm going to be going through is mainly taken from the Google documentation. It's basically the hello world of Tensorflow, and when I was experimenting with it, you can change sort of the problem that you're solving quite easily, which I thought was really cool, so I'll go through both of them. So what I'm going to do is I'm going to go through sort of what the output looks like first, just so that you can get a visual image of what we're going to be doing, and then I'll go through the TensorFlow code, and then I'll run it one more time with both types of data sets that you can do. So this is it's basically image recognition, and the two data sets we have are handwritten characters and clothes from a shop, basically. So this is basically an inverted color image of a handwritten 5. So where it's black it would be white, which I'll show you in a second, and then where it's very yellow here, that would be basically a black line, and then the color intensity goes from 255 to 0. Okay, so that's the first one we're going to show. So this is the first 25 numbers in our test data set, and what you have below that, the handwritten character, is the true label. So people have literally gone through every single image in the 60,000 and written exactly what the character is meant to be. So this 5 here is kind of dubious actually. Could also be a 6, but that's the true label is a 5, and basically we're going to see how sort of the neural network learns from this data, and even you can see how this task could get quite difficult, because look at these ones here, two different styles of ones. So it wasn't one person drawing all these characters. I think it was taken from a sample of like students and maybe university students as well, like school students and university students or something. People from different doing different things. So it's not all the same. Okay, let's continue. So now it's starting the training. So what we have is there are 60,000 training images, and then there's 10,000 images set aside for testing. And basically what we do is we sweep over the training data 5 times. So this is, right now we're on the second epoch. These are called epochs. And what it's doing is it's making predictions. It's comparing it to the true value, and then it's changing its basically algorithm or the weights and biases in the neurons such that the loss rate decreases. And then basically the loss rate is inversely proportional to the accuracy, so as you decrease the loss, the accuracy is going to improve. So we just finished the 4th epoch, yep. Now we're going down still. So you'll see now we're at about 98% accuracy, which is where this test and neural network like generally caps out. So yeah, we're not seeing much improvement now. Might get to 99%, might not. Whereas on the first epoch, so we get up to 88%, about a third of the way through the first epoch. 92%. So it's generally pretty amazing, but then you get like diminishing returns and stuff. So you're just kind of grinding out these last few percent. Okay, so let's see what else we have here. So this is basically same image we saw before. Then it has a percentage of how sure the neural network was that this was a 7, for example. So with the handwritten characters one, the accuracy is incredibly high, and this one it says it's 100% sure that it is a 7. So on ones which are more marginal, this would decrease, and there would be some other bars here, and then obviously sometimes an incorrect bar is higher than another. So it's certain this is a 9 as well. That's just an example. Some other ones. Okay, so this is the dubious 5 from earlier. So it still guessed correctly that it was 5 with 68% certainty, but its second best guess was a 6, 7, and then it could even possibly be an 8, but at a very low percentage. So I mean, I think that's kind of cool in that it can tell when something's marginal. But yeah, it still gets it right. Okay, so let's probably move. This was just some other testing I was doing. Okay, so that's basically the handwritten, the handwriting one. But I'll go through the TensorFlow code now. So yeah, we're just importing all of the libraries we need, just checking that. So I was basically going through this and running it sort of line by line to check it's working okay. So this just checks that TensorFlow's imported okay or running okay. Fashion, so this was originally the fashion one, but I've just changed fashion from here, so you could have fashion underscore mnist, that's the fashion data, or just mnist is the handwriting one. So I've just done mnist for the handwriting one for now. So we have the images and the labels, and then we have the test images and the test labels. So those are separate. So that's still the handwriting.load data, but that's fine. The class names, I'll swap these over for t-shirts and clothes in a second. So the class names for us right now was 0 to 9. Okay, this was just printing some stuff to the screen. So we were showing the shape of the data. Why does it show 60,000 here? Oh, okay, so it's showing how many, this is included in the shape, how many we have, and also the sort of length and the width of the array. So it's a 28 by 28 pixel grid, essentially. And yeah, so that's why it's included there. And we have the length of the train labels, which is also 60,000. So this is just sort of debugging me, getting a good image of what's sort of going on. Train labels, and then these are the final labels of what sort of classification they are. And then we have PLT, which is matplotlib, which I probably have used less than most people because I think it's very popular, but I normally just do loads of backend stuff. So that was just sort of the pop-ups that we're showing. Probably not going to dwell too much on them, just show the first image in our training set. Show the color strength on the right hand side, don't show overlying grid lines, blah blah blah, make it appear. Okay, so this is kind of important. So we saw the brightness was anywhere between 255 and 0, so we're dividing every value in the 28 by 28 array by 255 to standardize all the values between 0 and 1. That's for the training images and the test images. I'm just thinking about the test images because we're not touching them until the very end, but yeah, when we feed the test images into the neural network to make a prediction, they need to be in the same format as how the program was trained. So that's why they're both divided by 255. Okay, so this is us showing 10 images. Or maybe that's just the size, I don't know. Anyway, we're showing 25 images, 5 by 5 grid. We're not showing X-ticks. To be honest, I can't remember right now what X-ticks were, but I think they were the X-axis labels and Y-axis labels. Hide grid lines, show these. This just puts the color in binary, black and white. Yeah, I think so. And then we do have X labels here. I'm probably getting a bit confused here, but basically it wasn't very important. That's essentially what I'm trying to get at. Okay, so this is the TensorFlow neural network. So we're using Keras as the backend. Keras is basically used for its user friendliness. That's basically what the designers of it tried to do. So we're flattening the 28 by 28 grid into a so yeah, it has a length of 784, but it's just one line, so it's all just spread out into one line. That should be somewhat obvious. And then, so why do we do this? We do this, I think it's so that the model only has to work in one dimension. I think that would be easier. I guess it would be all the same, but I guess dealing with many multi-dimensional arrays would be harder. I don't know. I don't know the exact reason, but I know that this is what's done in. I've also done a Q-learning example, and we flatten everything there as well, even though you're dealing with two-dimensional arrays. So this just seems to be standard procedure, I guess, to flatten things into a single line of data. Okay, then So we go from a 784 input neurons to a hidden layer of 128 neurons. And this is basically where, I don't know, it's doing its sort of pattern recognition analysis. And basically we're slowly feeding forward down to the output layer of 10 output neurons, and then these 10 are the 10 possible categories it can be for the handwritten numbers 0 to 9. This softmax function basically means that all the output values, which could in theory be negative or they wouldn't all sum up to 1, but this softmax function adjusts them all so that they sum to 1 and they're in the range of 0 to 1. And then relu, I can't remember off the top of my head what this one does. I'll give it a quick Google now. A rectifier linear unit. Okay, I don't know I can't remember exactly what it is right now, but yeah, this is just a beginning introduction, shows how much I know, hey. Model.compile, so this is a choice of optimizer. I think it's one of the most default popular ones. It's a cross between two different learning functions, but my knowledge is not that great right now, so I'm not going to pretend it is. Loss, so I also changed this into just the highlighted text here, categorical cross entropy, and the neural network worked just fine, just because when I was reading the documentation it said if you're doing categories you don't need the sparse one, because there's basically two different types, but they both worked fine for me. Metrics, accuracy, so optimizer I think is the type of learning. The loss, I think this is something to do with how we categorize things at the end, but loss is also the mean squared error when we're doing the learning, which is like this number here. We're always trying to decrease it, but yeah, I'm not too sure on that one, so don't take my well, yeah, you might have to do some research yourself. It's very complicated stuff in my opinion. So this is the model.fit, train images, train labels, and we're doing 5 epochs, which is 5 sweeps over the data. So this is one of the variables you can change. So for example, in this one, 97%. Oh no, that's the test data. So we got to 98.5% in the final one, and then in the fourth one we're also that's about the same thing. So if you're repeating the test, we could easily reduce this to 4 epochs, and we won't have dropped much accuracy at all. Test loss, test accuracy. So yeah, this is the code which is testing on the 10,000 images which was set aside for our testing. And what you'll notice is the accuracy is slightly lower than our training data, which I guess is what you would expect, because when you're just sweeping over the same training data, although you don't want it to happen, the neural network's probably going to get better at doing images it's seen before as opposed to images it's never seen before. So I'd actually say it's quite impressive that we only dropped 1 percentage point into the test data, but the handwritten data is one of the easier ones based on the final accuracy. So yeah, this was just showing a prediction for the first image, and then argmax is just picking the highest value one, so the most likely label that the neural network wants to predict, show best prediction basically, and then just show true value. So this is this code here, which is like predictions. Yeah, so this is the predictions, and these are 10 to the power of 10 to the power of -1, so that's 99%, almost 99% certainty. Everything else is basically negligible. So it's guessing 7, the true label was 7, so that's correct. This is just a helper function. So we do have it where we flag in red if the predicted label is incorrect, not equal to the true label. We're showing percentage certainty, which we did do. Another helper function, that's fine. And then this is just showing 2 of the images at the end. and this is just showing more of the similar stuff, just showing some images and stuff. Okay, so now I'm going to run it through the fashion data. So I'm just replacing the MNIST dataset with fashion MNIST, and I think that's all I need to do. Okay, oh no, I need to do this. So I'm just commenting out the old category names. So what do these two datasets have in common? They're both 60,000 images of training data and 10,000 of test data. They both have output category, 10 output categories, and they are both 28 by 28. Every image is 28 by 28. So again, inverted image. This is going to be a shoe, an ankle boot as they call it. So this is, I think this task is a lot more difficult to do. For example, essentially the resolution is quite bad. Like even a human would have a really tough time saying that this is a t-shirt / top. That looks like a girl's top maybe. Could also be a dress, I'm sure. Well, sort of. Dress, pullover, that kind of makes sense. So what sort of patterns does a human use to identify whether something is a pullover or jumper, whatever? I guess that sort of like slightly thicker turtleneck could be it. Sneaker, that makes sense. Ankle boot, I mean, I would call that something else, like a high heel. I wouldn't call them sandals, I would call them flip-flops or something, but, well no, they're just high heels, you know, high heel flip-flops, but sneakers, sandal, I mean, that is just so blurry, that could be anything. And the same way we have a Nike tick here, that could be a bit of a logo or something, I don't know. I mean, I guess it is a hole, but yeah, I guess a lot of white space would be sort of the sandal flip-flop kind of thing. Very dark colors, I guess would be more ankle boot. Trousers, the white line down the middle and then surrounded by blackness, they would be identifying features. Coats, sort of the arm sleeves, bit of white space, might have a dark patch in the top middle somewhere. Bag is just a big block. Coat, I guess, has that sort of rounded shape. Basically, this could be a hard task, so I'm expecting, I think most people would expect lower accuracies. So this is an example of the data we're going to be looking at. So this is doing our first sweep over the data. And to be honest, even though I've run this simulation many times, I didn't pay close attention to how the accuracy changed from completing all 5 epochs over the training data and how the accuracy was on the 10,000 image of test data. So I'm going to pay close attention to that, because although I see that the accuracy does get pretty good in the training data, there might be quite a big drop off, but we'll see. So we're seeing it's getting 86% accuracy right now. One thing I did find sometimes happened was, so this is 86.5. Let's wait until we have a bigger sample size. What I found was that there tended to be a bit of a jump over the epochs. Like, so it might stagnate here. Let's go back 10,000. So it's like 86.5, whatever, 86.5. Let's do 10,000 of this one, 87. Okay, maybe I'm just imagining it, but yeah, so there's a chance I'm imagining it, but I've just felt like at the end of an epoch it would make a big jump in improvement, but I'm not sure what the necessary reason would be for that. Okay, so let's do a direct comparison. So 89% over the 5 training epochs, and then 86.8 in the test data. So that's pretty good. The drop off as a percentage is probably similar to, so that's 1% drop off, and here we have 86.8. What is that, 2.2? Yeah, 2.2 over 89. So it is a bigger drop off, 1% to 2.5%. I might have just botched that calculation, but oh no, it makes sense. Yeah. We have a larger drop off in absolute terms, and the number is smaller than before. So, well, I guess you would expect that, but yeah, it shows there's less certainty basically. So yeah, I guess that kind of makes sense. But I just think it's really cool how you can design one neural network, and then you can literally just change the input images and the category names, make sure the labels are all okay. You might have to change the output number of neurons and input neurons if the size of the data is different, but essentially you have one model which can do a multi-purpose job. So we literally just went from handwritten characters to clothes identification. So I just thought that was really cool. We essentially have a brain here which can learn to do basically, I don't know, 2 different jobs, I would say. But yeah, anyway, I hope you enjoyed it. I'm sorry I don't know everything completely inside and out. In particular, the relu, wherever it was, the activation function. I'm not going to go on a spiel now about it, but basically, yeah, I'm probably just embarrassing myself, but it will have to do with, I don't think it's to do with the weights and biases, but it might be. Activation. Because I think activation also has something to do with making sure all of the values go from 0 to 1 for the weights. Anyway, I can't really remember. I'll have to do some more research on it myself, but hopefully you enjoyed the tutorial. I'll slap the code on GitHub if you want to go through it and have a play yourself. And yeah, I hope you enjoyed. Alright, bye bye.